Good afternoon, everyone. Thank you for being here in our 5th plenary. Now, it is the time to present Professor Josep Nogués, our next plenarist. Professor Josep Nogués comes from the Catalan Institute of Nanoscience and Nanotechnology. ICREA research professor Josep Nogués earned his degree from the Universitat Autònoma de Barcelona in Spain in 1986. After obtaining his PhD at the Kungliga Tekniska in Stockholm, Sweden, in 1993, he moved to the University of California, San Diego to complete his postdoctoral studies. 4 years later, he returned to the Universidad Autónoma de Barcelona as an associate researcher, becoming ICREA research professor in 2001. He is, since 2006, the group leader of Magnetic Nanostructures group at the Catalan Institute of Nanoscience and Nanotechnology. Professor Nogués has published 254 articles, including 8 reviews, with over 19,000 citations and an H index of 59. He is the author of 6 patents, and his work has given rise to over 250 invited talks and international conferences and workshops. His research interests span from basic studies of the exchange and dipolar interactions in magnetic materials to biomedical, environmental, and mechanical applications of magnetic, magnetoplastic, and optic materials. Moreover, his group is also pursuing the limits of microscopy, synchrotron, and neutron techniques to develop novel approach to studying nanoscale objects. Professor will talk about the magnetoplasmonic nanodomes as a novel structure for biomedical applications. Welcome, Professor Nogués. To move the lights and the microphone here, or?
Thank you, Manuel, for the nice introduction. And also, I want to thank the organizers for inviting me to present our work in this nice conference. So, as Manuel said, I'm going to talk about your new structure we have developed for biomedical applications. So, before I forget, I'm actually the lucky one who has had the chance to come to Cancun to enjoy this conference, but this work has been carried out by a lot of different people. From my group, this is the work of mainly Ji Lee for the first part of the talk, and Aris Lafuente for the second part of the talk. And also, the last part of the talk, the in vivo work was done by Arnon Fuchsman and Ofra Beni at the Hebrew University of Jerusalem. We've also collaborated with the Universitat Autònoma de Barcelona, with the groups of Jordi Sort and Carme Nogués. And the first part of the work was done by their PhD student, Toni Aranda. And we also collaborated with Universitat Pública de Navarra, Alberto López, and Nanogune in San Sebastián with Paulo Bassori. But actually, the main person in this work is my colleague, Borja Sepúlveda, who used to be in my group, but he moved on into the Microelectronics Institute in Barcelona. Well, as you all know, nanoparticles have been used or have been proposed to be used in many different fields, like ranging from industrial applications in electronics or memories, or in environmental issues. What else do I have here? In energy storage and all kinds of different things. But one of the most popular topics for magnetic nanoparticles is biomedical applications. And why is it interesting? Why are nanoparticles interesting for biomedical applications? Well, the size of nanoparticles, say from a few nanometers to some 100 nanometers, are in the same size range as many biological entities, like a virus or DNA or things like this, and they can also easily interact with cells, which are slightly larger than the nanoparticles. There are many different applications of nanoparticles in the biomedical field. I mentioned here a few, from therapy, sensing, nanochemistry or toxicity. And actually, in my talk, I'm going to touch a little bit on drug delivery, bioimaging, cancer treatment, and biosensing. So, one type of particle that has been extensively used in biomedical applications is magnetic nanoparticles. Usually, the one which is mostly used is iron oxide, or different types of iron oxides, because these are the only ones that are approved by the FDA. But iron oxide nanoparticles have a problem. I try to illustrate it here. When we make small nanoparticles, these ones are 16 nanometers. As the base state, they are colloidally stable. If we make them slightly larger, like 20 nanometers, in the base state, they are also colloidally stable. But if we wait a few days, the 16 nanometers, they are still stable. But the ones, the 20 nanometers one, they precipitate. What happens is that with time, they agglomerate. We can see this very, very clearly. This is the ratio of the TEM size by the size measured by light scattering, which the light scattering gives the size of clusters if they are formed, not the size of the nanoparticles themselves. And we see here that if the particles are small, the ratio is 1. The ratio of the size of the TM size and the DLS size is the same. But as the particles become larger, the light scattering size starts to increase, meaning that these particles have agglomerated. And when they agglomerate, their properties usually worsen. And actually, they cannot flow in the biological media as easily as single nanoparticles. And why is that? When the particles are small, sorry. When the particles are small, the hysteresis loop here, well, the particles have no stable moment. The moment fluctuates with time because the energy, the anisotropy energy of the nanoparticle, the magnetic energy, is of the same order as the thermal energy. That makes that the magnetic moment fluctuates with time. And what happens is that at zero applied field, it has a zero moment because the magnetic moment fluctuates all the time. So that makes the average magnetic moment to become zero. And when the particles are larger, then the magnetic moment is stable. And then we have a typical hysteresis loop shown in green here. But what happens when the particles are large? Then they have at zero field, they have a large magnetic moment. That means that they can interact with each other magnetically by dipolar interactions. And the lowest energy state is that they agglomerate and form clusters. So, but the other problem is that you see here, when the particles are small, you need a very large fields to get a sizable moment to be used in applications. So we have an issue. So we have an issue we need to solve. So that's That's what I'm trying to do, we're going to tell you about in this talk. We designed this new type of nanoparticles that we call nanodomes. And what they are is a polystyrene bead, which is, we buy a commercial beads with about 100 nanometers. And then we cover them just by a dome with iron and gold on top. Why did we choose these two materials? Well, gold has a localized surface for surface plasmon resonance, which I will show you that we can use for local heating. It has a high atomic number, which can be used for X-ray contrast tomography, and it's very easy to be biofunctionalized. And iron has a high magnetization and has a magnetic resonance, strong magnetic resonance, which can be used for MRI. And because of the high magnetization, it can be easily manipulated using magnetic fields. Sorry. And what we want to do with this is that we want to magnetically control these nanoparticles to do photohyperthermia using near-infrared light. So what's this photothermia? As the first plenary speaker, Luis Marsan, told us, gold nanoparticles have a plasmonic resonance. What it means that when they are irradiated with light, they create an electron cloud that fluctuates. And when we can get the resonance of these fluctuations, there is a big absorption of light in the nanoparticles. And shown, these are the absorption peak. And this absorption, this resonant absorption, depends on the size and the shape of the nanoparticles. And we can tune the wavelength at which this absorption takes place. And what happens is that this absorbed light has to be released somehow. And the way it does is it releases, it warms up and releases heat. And we can use this to locally heat the sample. If we with a near-infrared light, we shine laser somewhere where you have nanoparticles, we can locally heat that area and not the other areas. Even if the laser pointed in another place, if there was no nanoparticles, there would be no heating. And why is it important to use near-infrared? Because near-infrared is the so-called biological window. What it means is that in this region, the body absorbs the least amount of light. So light can penetrate much deeper in this region than in the visible light. And that is very easy. If I do this with a green laser, nothing comes out. If you try the same with a red laser, you'll see the spot here. So meaning that as we go to the infrared, more light penetrates into our body. So how do we go about to do nanoparticles? I'll switch sides for a while. So as I told you, we buy our polystyrene beads for 100 nanometers, and then we electrostatically self-assemble them on a surface. Usually we use silicon, but we've tried other types of substrates. So here how it looks when they are assembled on a surface. And then using electron beam evaporation, we evaporate the two layers, the iron and the gold on top. And then, if necessary, we can functionalize the nanoparticles as they are on the wafer. And finally, using ultrasounds, we release the particles from the substrate, and we can transfer them to water very easily. Here I show you a TM picture of how this looks. We can see very clearly the polystyrene bead on the bottom, and on top there is the metal layers. Using this approach, we can do, using a 4-inch wafer, we get about 1 × 10⁻11 particles per wafer, which is about 600 micrograms of sample per wafer. And this approach has several advantages. First, that we fabricate in vacuum, meaning that we don't need any toxic solvents to have our nanoparticles, in contrast to iron oxide, for example, where you use chemical synthesis. We can functionalize directly on the wafer, this step here. And it's very easy to disperse the nanoparticles in water. We don't need any exosphere, just ultrasounds. And as I will show you later, using this approach, we can tune both the magnetic and optical properties of the nanoparticles. To make sure that we really have our the structure we designed, we did some energy loss spectroscopy mapping in the TM, and you see here the TM picture I showed you before. And when we measure at the gold edge, we see a big shell here. When we measure at the iron edge, we see that the shell is smaller. So when we overlay the two images, you see that we have an iron shell, and on top of that iron shell, we have a gold shell. So we indeed have the structure we designed. So then we went on and measured the magnetic properties. And what we did is to keep the total thickness of these two layers constant at 40 nanometers, and then we changed the ratio. We went from 5 nanometers of gold, 35 nanometers of iron, 10 nanometers of gold, 30 of iron, and so on. When we measure the magnetic properties, we see that when the iron is very small, we have hysteresis loops similar to the ferromagnetic nanoparticles I showed you in the beginning. So they have a remanence, they have some moment at zero field, meaning that these nanoparticles could interact with each other and potentially agglomerate. But when we have thicker iron layers, like 20 or 30 nanometers, you see that the hysteresis loop changes. And now what we have is what is called a vortex structure. Instead of having all the moments pointing in one direction, as you would expect, now, due to the competition between magnetostatic energy and exchange energy, the most favorable state is a state where the magnetic moment rotates around the circle of the particle. And in this way, you have zero moment at zero field. As we can see here in the hysteresis loop, they have zero moment at zero applied field. That means that these nanoparticles at zero field, they don't interact with each other, so they do not agglomerate. And this we can see in the light scattering measurements. You see that the size we get from the light scattering measurement is 130 nanometers. That is 100 nanometers of the polystyrene bead plus the 40 nanometers of the shells. And also we get 20 millivolts zeta potential, meaning that it's a stable colloidal structure. So since we have minimal dipolar interactions, we have a very, very high colloidal stability. But, of course, now we have iron and we have a big particle. So in terms of magnetic signal, 1 nanodome is about 500 times more stronger than 10 nanometer iron oxide nanoparticles. That makes that these nanoparticles are very easily manipulated using magnetic fields. Here I show you the optical properties of the nanoparticles. Here I show you the absorption. Well, it's actually, this is the extinction, which is the absorption plus the scattering. And we see that when we change the ratio of gold and iron, the extinction shifts to higher wavelengths and the intensity decreases. And then what we do is, okay, can we use these nanoparticles for warming, for photothermia, for kinetic heating? And what we did is to put the nanoparticles in suspension, and then we shine 808 nanometer laser on them, and we have an infrared thermometer measuring the temperature of the liquid, and then we measure how much light goes through the dispersion. And I show here the typical experiment. You see, we put the laser on, and the temperature starts increasing, and then we switch off the laser, and the temperature goes down. And we see that in a few hundred seconds, the liquid can increase 20 degrees very easily. And the heating depends on the concentration of the nanoparticles, but not so much on their actual structure. You see that the heating is similar for the pure gold or the gold iron nanoparticles. So we have a very strong photothermal effect. And actually, these nanoparticles can be also used for biomedical imaging. Here I show you some magnetic nuclear resonance, TD contrast. You can see here the T2 signal, and we have an R2 of about 266, which is, I don't know, 50 times, 100 times larger than the commercial iron oxide nanoparticles. And you can see here some in vivo imaging. You can see here, this is the liver, I think. And it is gray here. And then we put the nanoparticles, it becomes black, meaning that the nanoparticle, the iron, the nanodomes can be used for imaging of in vivo also. And then what we did is some X-ray microscopy of these nanodomes inside cells. Here, these are the organelles of the cells. And here in black, you can see the nanodomes. The fact that they are so black, it means that they absorb a lot of X-rays. This is interesting for computed tomography. Although we have not tried, it should also work similar to what MRI showed. And then another thing we did is to change our polystyrene beams by fluorescent polystyrene beams. And then we used confocal optical microscope to see if we could see the particles. And indeed, you can see the red dots inside the cell. These are our nanodomes inside the cells. And then with the confocal microscope, we can do slices, and then we can project them. And you can see here that indeed the nanoparticles were inside the cells when we do the projection of the confocal imaging. And then we wanted to make sure that these nanoparticles could be manipulated using magnetic fields. So we made a simple a microfluidic system where you can see here, this is a magnet, and here we enter the liquid goes on top of the magnet and then goes out on the other side. And what we did is we measured the optical absorption on this side before they go through the magnet, and then we measure again the optical absorption after they go through the magnet. And in that way, we can know roughly the concentration but just by looking at the change of absorption, optical absorption. And we can see here that, and then here you can see we inject this at a controllable speeds. And then you can see here that in a single run, using nanodomes, we can trap almost 80% of the domes in a single run in using this structure. And when we increase the speed of the fluid, then the trapping goes down, but still it remains around 30% even for very high fluid speeds. Know that the blood in mice runs from 90 microliters per minute to to 1800 microliters per minute. So this is faster than what the blood would run. We did the same experiment using 14 nanometer iron oxide nanoparticles. And you see here that even at very low speeds, our trapping efficiency in this case is less than 10%. So this demonstrates that our nanodomes are much more efficient to be manipulating using magnetic fields than iron oxide nanoparticles. Because, as I said before, the total moment of our nanodomes is about 500 times stronger than the total moment of an iron oxide nanoparticle. So then I wanted to see, okay, can we manipulate the heating using the magnetic field? And what we did is to, the same as we did before, we put our liquid in a suspension, and we have our infrared thermometer here. But now we put a magnet in different directions. If we put a magnet in such a way that the particles are pulled away from the optical path, that's the experiment here, you see that when the particles are in the optical side, the power that goes through is relatively small, and the temperature is high. But let me see. This is the normal experiment without the magnet. The power that goes through is small, the temperature is high. And then we put the magnet that pulls the particles away from the optical path. Then the intensity going through increases because there's no particles absorbing light, and the temperature goes down. And then if we do the other way around, now the laser is going in the same direction of the magnetic field, so now we concentrate our particles in the optical path. So in this way, now the heating in the beginning is small, then we put the magnet on, and we increase the heating considerably just by concentrating the particles in the optical path. So we can have magnetic enhanced heating using this simple approach. So then we use this to try in vivo. And we had some HeLa cells on a cell culture, and we put nanodomes with 20 iron, 20 gold. And then we tried with a magnetic field, with light without magnetic field. And then we tried different combinations. So when we have light and magnetic field without particles, nothing happens. All the cells survive 100%. When we put nanodomes with magnetic field only, nothing happens. When we put light with a small amount of magnetic fields, 10 micrograms, there is a small decrease already of cell viability. When we increase the concentration to 100 micrograms per milliliter, there is a little bit, and the laser on, there is a little bit more cell death. And now when we concentrate the particles with a magnet, with a laser on, with 10 microliters after 24 hours, there is a considerable decrease. But if we wait for another 24 hours in these conditions, we see there is a large decrease on the cell viability. But when we try the same with the 100 micrograms per milliliter, we see that already at 24 hours, there is a large decrease in the viability. So to understand what was happening, this is the cell counting. Before this, in green, all the cells are alive. After the laser, all the cells are dead. But then we did an SEM of the samples, of the cells. See, this is before treatment, and this is the treatment with 10 micrograms per milliliter, and this is the treatment with 100 micrograms per milliliter. You see here that when we use 100 micrograms per milliliter with the laser and the magnet, we literally fry the cells. This is not good because these cells have died by necrosis. Necrosis is bad because it has bad side effects on the healthy cells. But when we use 10 micrograms milliliter, the cells, you see that they change morphology, but they still look like cells. This is because they are dying by apoptosis, which is a type of cell death which is much more controlled and has no side effects. So this difference made us the question, what's the actual temperature during the treatment? Why these ones were dying by necrosis, why these ones were dying by apoptosis? So we designed a new experiment to see, can we really measure the temperature inside the cells? So what's the temperature to the cells? So what we did, we designed a new type of nanoparticles. This time, instead of having iron and gold, we made a multi-layer of cobalt and gold. These nanoparticles have an autoplane magnetization and have a much stronger magnetic anisotropy than our previous nanodomes. So, and then what we did is we measured the transmission of these nanoparticles. So we put them in suspensions before. We shine light and measure how much light goes through. But now in this case, now we have a magnet in our system. And we can see here when the nanodomes are randomly distributed, they have this black curve here, sorry. And now when we put the magnetic field and the nanodomes align, we have this blue curve here. So there is a huge change in transmission just by ordering the particles. So we are going to use this optical anisotropy to use as temperature sensor. So what we did is to, instead of having a static magnetic field as we did here, now we put an AC field. And here you see that the optical signal is twice the magnetic field. That is because optically the nanoparticles are the same when are in this way or in this way. So we have a second harmonic response to our magnetic field. But most important is that since the particle is inside the liquid and there is some viscous drag inside the liquid, the particles cannot follow the magnetic field. And there is a phase lag, shown here in this difference, between the frequency of the magnetic field and the optical response. And actually, this phase lag depends on the viscosity of the medium. So since the viscosity decreases with temperature, then we can use this change of phase lag, which is because of viscosity, to measure the temperature by calibrating the system. And that's what I did here. We have our system I showed you before. Now we have the infrared thermometer, but now using a Peltier system, we controllably change the temperature of the system. And now we measure the phase lag in the system. And you see here, in black is the temperature measured by the infrared thermometer, and in red is the phase change because of the viscosity. And you can see there is a one-to-one correlation. So we can use this phase change to actually measure the temperature of the liquid. And using this approach, we can have a detection limit of about 0.05 degrees. And then, can we actually do the same using the laser? Can we warm up and measure at the same time using the nanoparticles? And here I show you the actual measurements. We put the laser on, and we measure with an infrared thermometer and using the phase lag of the nanoparticles. And we indeed, both systems follow very nicely the same trend. The difference in temperature between the two systems is because the infrared thermometer is measuring the temperature at the surface rather than the temperature around the nanoparticles as the phase lag does. So that's why there is a small difference in temperature, because it takes some time for the heat generated at the nanoparticles to reach the surface, which is what is measured by the infrared thermometer. And a nice advantage of this is that this approach using the nanodomes is much faster in response than the infrared thermometer. And here, what we did is to have laser pulses of a few seconds each, and you see that using the nanoparticles, we can nicely follow the pulses of the laser, while the infrared thermometer just feels the accumulated effect after a few seconds. So with the nanoparticles, we can really measure the local temperature of the liquid surrounding the nanoparticles. So we were encouraged by all these results, so we decided to try in vivo. So I'll go to the other side for a while. So now, to do the in vivo experiments, we changed our structure slightly. First, instead of using polystyrene beads, we changed to biodegradable PLGA beads, which actually we filled with an anti-cancer drug, it's a PCX. And now, instead of using gold, we use silicon oxide as a capping layer. This is because we found out that iron actually is plasmonic. It's not as good plasmonic as gold, and it has what is called a damp plasmonic behavior, but it still can absorb light and generate heat with the iron alone, without the need to put in gold, which is expensive, and you don't want to waste these kind of materials. And actually, as I'm going to show you, this approach, using iron alone, it also has a strong photothermal effect. So first, what we did in the vivo structure is to check the effect of the drug. First, we check the cell viability using only the PLGA beads, without nothing inside, or without the nanodomes, and there is no change. When we use the nanodomes, there's a slight change, but there's no statistical significance. When we use the PLGA bead with the drugs, it does have a reduction of cells, meaning that the drug works even if it's inside the PLGA. And the same, when we do the full nanodomes with the shell, the drug, and the PLGA, it also still, the drug still works and kills the cells. And then we tried the optical heating, and you see here that when we use the laser without magnetic concentration, we can reach an increase of temperature about 20 degrees. But when we do magnetic concentration, the temperature increases even further, because now, as I showed you in the in vitro experiments, we concentrate the light, we concentrate the nanoparticles in the optical path, and that makes it that they are more efficient. And then we tried in vitro the photothermal effect. Here you see that this is not without any just the cells. And then this one is with magnetic field without laser, with laser without magnetic field, and there is no change. And then when we put the particles inside, since they have the drag, there is a decrease in cell viability just because of the effect of the drag. And then when we put the laser on, there is a further decrease in the cell viability. And when we do the magnetic concentration, there is an even further cell viability decrease in the in vitro experiments. And here, using fluorescence, we can see the distribution of the effect in the cells, where they die, so to say. And you can see that when we don't have the laser on, the effect is quite homogeneous everywhere. But when we do the magnetic concentration with the laser, the effect is concentrated where we have the laser, meaning that we've managed to concentrate the particles in a certain area, and then they increase the effect in that area. And then we studied the biodistribution using MRI. And you can see here, we have the liver, the spleen, and the kidneys. And you can see here that the ones becomes black, meaning that the particles go to that area. And here I show you quantification. That the signal decreases, it means that they're gone to that area, meaning that the particles concentrate in the liver mainly, and also in the spleen, but they don't go to the kidneys. But what's important, as I show here in the top, after 72 hours, we gain again the same signal as in the beginning, meaning that the particles have been cleared from the body of the nanoparticles after 72 hours. And also we did we checked the organs before and after the putting nanoparticles in them, and there is no major change, meaning that the particles have no effect in the organs. And then we did some in vivo tests. First, it's important to mention that we use an ultra-low concentration of both nanoparticles and drugs. We use only about 8 micrograms of Plaxitel for gram of weight of mice. This is about some hundreds times less than what is usually used in vivo experiments without nanoparticles. And then what we did is to put for 2 hours a magnet close to the tumor to concentrate, and you can see that up here. In yellow, that's the tumor, and you see before it's all gray, and after 2 hours it becomes black in here, meaning that we concentrated all the particles in the tumor. Then we try we use the laser on the tumor, and you see here that the laser itself on the tumor increases a little bit the temperature. That's the green curve here. When we use the nanoparticles and the laser, the temperature is increased further, and when we do the magnetic concentration, which is this one, we can increase even further the temperature. So to do the experiments, what we did was a single 20 minutes laser actuation at 808 nanometers. And then we checked the tumor size and volume with time. You see here that if we don't do anything to the mice, that the tumor grows uncontrollably. when we use the laser alone without any particles, there is already some improvement because of the laser itself generates some heat. So that heat is already good to remove part of the tumor growth. When we use the nanoparticles and the laser without concentration, there is a further reduction of the tumor growth. But when we use the magnetic concentration and the laser, you see that after 15 days, we can completely remove the tumors from the mice. So the drug-loaded nanodomes with the magnetic concentration and the near-infrared laser are very effective in eradicating the tumor, even at ultra-low concentrations. So to conclude, I hope I have convinced you that we have been able to grow some strong nanomagnets, which are good nanoheaters, which can be used for multimodal imaging, with NMR, computed tomography, and fluorescence. And they have a very high efficiency in photothermal therapy by magnetic manipulation. I've also showed you that we can design nanodomes with high magnetical and optical anisotropies, which can be used to detect viscosity and temperature changes with very high sensitivity. And we can simultaneously use the nanoparticles both to heat and to measure the temperature, even in cell dispersions. And also, the last part of the talk, I show you that using biodegradable drug-loaded nanodomes, we can be used for in vivo therapy. And the drug-loaded nanodomes with magnetic concentration and near-infrared laser are very effective in eradicating tumors in mice. So thank you all for your attention.
Thank you so much, Professor Josep Nogués, for this fantastic talk. I think this is a very, very interesting topic about these nanodomes for biomedical applications. And I'm sure that the application of these structures could be very useful in future to eradicate these cancer cells. And now we have some time for questions. So please, if you have a question, raise your hand. Here, please.
Thank you. At the last part of your talk, you showed that you do not need gold. Mm-hmm. And then you say that the highly damped plasma of iron is enough. Mm-hmm. I'm surprised because the plasma of iron is quite in a different energy range. Usually use gold because it's indivisible. Yeah. And then the secret is that you are depositing the iron in vacuum, then it is metallic iron, yeah. It's not the oxide. Then if you do the thing with metallic nanoparticles, you also, that is the difference with the conventional yeah. oxide nanoparticles. Yeah. But there is nothing chemical about having metallic iron in the reaction of the tumor.
If we had iron oxide, we would not have a plasmonic resonance, even a damped one. It's gone, my presentation. I cannot show you.
Thank you very much for your wonderful talk. Is already somebody doing some experiments in humans?
No, we are not planning, and there is some experiments in humans using plasmonic nanoparticles, using gold nanoparticles. Using our things is too complicated to go into humans. Although our Israeli colleagues are looking into that, but for us, in our institute, we cannot do these kind of things.
Other questions?
Nothing to do with medicine. How have you verified the circular arrangement of the spin? Have you used holography or which high-resolution technique to check that in a nanodome with it? Have you verified that?
No, you could do that with using magnetic force microscopy, for example. But we have not tried. No.
Okay.
But the well, they say not the shape of the hysteresis loops. That's definite. There's no question about it.
We have time for another question. Well, I have a question, Professor. Regarding, you mentioned something about the elimination of these particles after they made their work. I think you mentioned 72 hours after that. And how can you be sure that all the nanoparticles are eliminated from the body?
Well, that we cannot be sure. We can be sure that we cannot see them by NMR, by MRI. That we can be sure. But what happened to the nanoparticles if they are metabolized and go to, that we cannot know. We're actually working on analyzing, for example, the urine of the mice and see if they really get rid of the iron, or if it stays in the body but metabolized.
Okay.
But as we are now, we don't know for sure where it goes, the iron. For sure, we cannot see it with the MRI.
Okay, thank you. An additional question here, please.
Have you tried to remove the polystyrene particle and see how the signals change? Because when you do the drug delivery, these particles with the drug are released, right? And how the signals of the plasmonic system change?
It actually changes because as the PLGA is degrading, it starts oxidizing from the bottom. I'm not sure. I don't think I have a but that is also showing us that the particles, the shells themselves are degrading and also disappearing from the system, because the plasmonic properties, the optical absorption in this case, is changing with time and eventually disappears also, because the metallic iron is oxidizing to iron oxide, and then it's metabolized by the system. And actually, the magnetic signal also goes down with time because of the same reason, because it goes from iron to iron oxide to disappearing.
No more questions? Well, let's thank Professor Josep Nogués for this wonderful talk and for sharing us his research advances.
Yes, sir.
Thank you so much, Professor.
sí, sí, ok. Ok, check, check, 2, check, sí, ok. Ok, 2, sí, 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 ok. Sí, check, check.